Guten Abend. Wir freuen uns, dass fast voll ist. Wir haben den zweiten Vortrag heute in unserer Vortragsserie Affekt. Und wer gestern schon da war, ging sowohl gestern als auch heute um Klima, um Energie und ökologische Themen. Gestern ganz anders, glaube ich, als heute. Aber wir freuen uns sehr, dass der Stefan da ist, den Vortrag hält. Stefan ist schon viele Jahre am Institut zusammen mit dem Volker und wir freuen uns, dass du jetzt wieder da bist als Gastprofessor für länger und für die kommenden Jahre. Stefan ist, wer Transsolar nicht kennt, der wird es heute kennenlernen. Geschäftsführer von einer der Niederlassungen von Transsolar, nämlich in München. Ursprünglich seid ihr aus Stuttgart, also eine deutsche Firma, die aber weltweit tätig ist und weltweit das Thema KlimaEngineering oder Energy Design, würde ich sagen, auf dem allerhöchsten Niveau vertritt. Ihr begleitet wahnsinnig viele internationale Projekte, sehr wichtige Beispiele wie Energiedesign in Architektur oder mit Architektur zusammenspielen und Konzepte umgesetzt werden, und du wirst uns das heute erzählen. Machst du seit über 30 Jahren, oder?
Ja, also Energie über 30 Jahren, Transsolar über 27 Jahre.
27 Jahre. Und ja, danke, dass du da bist. Ich glaube, ich gebe einfach das Mikrofon an dich. Und die das Seminar besuchen oder die das Seminar in den letzten Semestern besucht haben, kennen dich eh. Aber ich glaube, heute ist auch die Einführung für das neue Seminar, was morgen beginnt. Danke, Stefan.
Danke, Caroline. Gut, ich möchte über KlimaEngineering, die Klimakatastrophe und Lösungen daraus sprechen. Ansatz und Beispiele, Integrated Design für High Comfort, Low Impact Buildings. So ein bisschen thematisch einleiten. Ich habe eine Grafik gefunden. Okay. Hi. Das ist eine Grafik über die CO2-Werte. Sollen wir wechseln? Okay. Okay. So this is the history of CO2 concentration, CO2 concentration in the atmosphere in parts per million, ppm. And this is dating back to 800,000 before Christ. And for all these years till now, it has ranged from like less than 200 to 250 and back. So all the ice ages are in that. And now it went up to 430, and that is not the end. This is 2021. We're at 440 now. So there is really something that changes at this level. And what it's doing is this: droughts, heavy rains, flooding, thunderstorms, tornadoes in Europe and in moderate latitudes. So we have to do something against that. We have to reduce carbon emissions to zero and fast. Because I did a little study on Germany's budget, and I'll show that in a minute. But the other aspect is that not only these catastrophes, but also standard living conditions. This is Abu Dhabi in 40 degrees summer. And you see our cities are even hotter than the air around us. So surface temperatures of almost 60 degrees in a street. And the the building surfaces also are very hot. So we have to do something to our city climate. And I will, in the very end of the talk, also show what can be done there. This is about rating this a bit in worldwide dimensions. We have the big emittance of carbon dioxide, which is China and the USA now. This is current 2020 data. And Germany is about the 2% of that. But as you can see, 2/3 of that are only 10 countries. All the rest of the world is the remaining third. So if we want change, then we have to change, not the rest of the world, because all of this is relevant. And if you look for Germany and see how our carbon emissions went down over time, since the 90s, we had kind of a decrease of about 1% per year. And then I added to this graph the Corona times. It went down faster, but then it went up again. So with the economy picking up after Corona, we're back to that 1% curve. What we need is something that is 5 to 6 times steeper going down, because that is the remaining budget that we have, almost 5 gigatons of carbon emission, total carbon emission, to not get over 2 degrees increase in temperature worldwide. This is the 2% part for Germany over the next couple of years. So if we do this, we would come to 2 degrees. We probably won't make that, and the rest of the world either. So we will have to face temperature increase over 2 degrees, 3, maybe 4. And that is rated as the whole globe. And we have water, a lot of water, and we have land. And that's the average temperature increase. So over land temperature increase in Germany is about twice as much as the global medium. So we will have to face here in our latitudes something like 4 or 5 degrees. And that is creating all of this probably as a standard. So looking onto the building sector in Germany, we're almost 40% of all that problem is coming from buildings. So I think we as architects, engineers working in the building sector can significantly contribute to that decrease, or we can just leave that. So it's also our responsibility to do something. And we at Transsolar have developed this pretty simple strategy of 1, 2, 3, 4. One is looking at the city configuration, building massing, leaving enough space between buildings, optimizing for daylight, solar energy, and Außenkomfort, outdoor comfort. So that's city climate, microclimate. Then once we have buildings, we need to minimize the energy consumption and bring that down significantly. But looking on this, it's not only bringing the heating demand down and insulating buildings at the max, it's also looking on electricity, on cooling, and it's also combined with 3, which is energy efficiency of energy supply systems. So 2 and 3 as one thing need to be optimized. So sometimes it means do a passive house. Other times it means do something that's naturally ventilated and doesn't use so much electricity, especially for air transport. And then once we've done that, we need to maximize the amount of renewable energies on the building side. And if that is not enough, then also external. So it's a pretty simple strategy, but it comes with a lot of details. So all of this, bringing that carbon footprint down, means you have to work on the building envelope, insulation, daylight, shading, selective glazing, ventilation systems, natural ventilation, nighttime cooling, hybrid systems, mechanical ventilation, natural ventilation, and also always, demand controlled, not on off. It's always good to have something that is reflecting the building use and not just ignoring that. Then the internal gains of the users, they are a big part of the problem, you'll see later on. So we also have to talk to building users, clients, to say, you can't expect that the building does it all for you and you just use your old machines and leave them on. So they have to do their part. And then the rest is more of like local resources. So geothermal use, water, what is there in district supply systems, and what type of renewable energy we have at the certain site, where are we in the world? And then one more topic is construction. Because if we only talk about operational energy, Betriebsenergie, then we forget one thing is like, where do we construct our building from? So all the building materials and their emissions also go into the equations, and we need to minimize that too. And therefore, it's quite a problem. And then there's something that is interesting. So that path down that needs to be very steep is only energy and carbon emissions. And we want to get as fast as we can there, and hopefully get new buildings with negative emissions to contribute to the overall reduction. But we also have people in these buildings, and they want to have like a warm or cooled building. They want good visual comfort, enough daylight, no glare, good air quality, acoustic comfort, and also have the ability to interfere with the building systems. So we want this comfort, but we don't want all the technical effort and all the energy consumption associated with it. So low-tech systems are good because they use less material, but they have to be clever to provide all of this, maybe slightly different from what we've been used to with mechanical operated systems, but to a similar degree. So if you look into codes and DIN norms, comfort and all these quality aspects are rated. They come in classes. And the typical client for a new building says, for me, it's easy. I always take deluxe. I want AAA, everything best class. And then if you really read, you see, okay, class A, and that temperature range is only like for recommended for hospitals, not for standard office space. Standard office space, class B is fine. So just ignoring the fact what type of building you have might bring the emissions up. And then there's research in the world. That study, which you almost can't read, is productivity rated against the ability to have certain conditions in your building. So the increase of productivity, if you have operable windows, if you have enough daylight rather than just artificial lighting, if you have control, good air quality, is like in the range of 10, 15% better than in a standard building. So it means if your user of a building has some access to interfere with building systems, typically they are happier and more productive. That comes as a unit. And we've done some research for the European Patent Office in Germany and in the Netherlands. And in the Netherlands, they have a Nouvelle building, highly glazed, super nice building, but completely air conditioned and fully controlled, no operable windows, floor to ceiling glass, sealed from the environment. In Germany, at the train station, they have like the opposite. It's a simple building, naturally ventilated, some cooling devices at the ceiling in meeting rooms, and that's about it. So if people enter the room in the Netherlands, they see a machine. So they expect perfect climate, AAA conditions. And if they don't get it, or they think they don't get it, they complain. Write a complaint report, and they had tons of complaint reports in the Netherlands. And then they were researching how many complaints about indoor air quality, humidity, temperature deviation they had in Munich. And in Munich, you enter that room, you see operable windows and nothing. So you don't expect any humidity control. So we went through their data over 10 years and looked what's the percentage of complaints about humidity, air quality, and wrong temperatures? It was 2%. In The Hague, it was more than 50%. So even though they invest much more in this building to air condition it, they got more complaints than a building where They just let the natural forces do it. And people don't expect that. So it's really related to people. And I think that is something that we more or less developed as a principle, saying, we don't want these boxes anymore, sealed from the environment, Fenster zu und voll konditioniert. We want open environments and different climate zones within the building. Radiant systems rather than air systems, operable windows, shading systems that are operated by the users, and balconies and loggias and areas where you have a different climate in the same building. And then that is more well-being and more productive than these sealed boxes. So whenever we have clients approaching us to develop a concept, we say, well, we have to, find our project rating between high tech and low tech. High tech, everything is guaranteed, but there's a big machine that guarantees that. Low tech, things are wider bands, more swinging. You have less equipment, you have less energy normally, and it's way more robust. If something fails, then it's still comfortable, somewhat comfortable, while in a building that has just high tech and mechanical systems, if these things fail, you're in bad shape. So that is more like the target. So looking a bit back in history, that is the Flatiron Building in New York, Manhattan. In the 20s, it's got a climate adaptive building envelope, because what you see here in a high-rise building is operable windows and external shades. That was before somebody invented a chiller and the air conditioning. So that worked in a way. It was hot, but they had cross ventilation. It kind of worked. Today, it all looks like this. So only sealed facade, reflective glass, no operable windows. You're in that box. And if something fails, you have to get out. And it doesn't even reflect where you are in the world. Dubai is really hot, London is not, same facades. So we have to change something here. So relating this a bit to the global problem of carbon emissions, this is Asia. And in Asia, we have over 270 cities with more than 1 million people living there. In the Americas, it's 80, in Africa, 60, in Europe, around 40, in Oceania, 6. So there's way more city life in the Asian countries. In the next 15 years, we will have 85 billion square meters of additional space in cities that are either renovated or built new. And we have to do something about that. So 60% of all that is in Asia. And that is in hot and humid and tropical climates. So talking about passive house, thermal insulation here is a minor part of the problem worldwide. Worldwide, we need to talk about what to do in a tropical climate to not run the air condition day and night. So the way we build our buildings with these facades and the way we define comfort, is it only temperature or are there other aspects, will have significant influence on our climate. And that's global, worldwide. So we need to develop principles and approaches that are not only good for moderate climates as we have them, but also for tropical climates and all the extremes. So just showing a couple of examples that we did in the 30 years we have been working as Transsolar. Some of these buildings are known, others are not that much known. Some of them have a label that's calling them climate positive, meaning they in operation reduce more carbon in the atmosphere than they generate. Some have different approaches to them, and we're doing what we do, this type of KlimaEngineering and all these developments for 30 years now. And that was last year's party with the whole company trying to build 3 days with our hands things we always just talk about. Pretty interesting experience, and a lot of knowledge transfer from outside to inside, from old to young, and reverse. And now just a variety of examples of buildings that we did in the past. And I want to explain this approach to energy and climate conscious building development in a couple of examples. So this is a very old example, 20 years old. The Munich Re high-rise building in Munich, together with Alman Sattler-Wapner, finished in 2003. And the idea was to actually have a facade concept that allows natural ventilation, that protects the shading from the wind, because we have strong winds in Munich, and that provides operable elements, like at all office spaces in all directions, for people to naturally ventilate. And they can ventilate the top window, which then generates some preheating of incoming air by its solar radiation. And they can open a lower window here in summer when you directly want this ventilation coming in through this perforated metal that is part of the exterior envelope. So then we thought, okay, now this is what you do individually, but with what about the standard system, which is typically a mechanical ducted shaft system to provide fresh air to the office spaces? And we said, why not use the height of the building as the stack to drive a ventilation system that doesn't need a fan? Kein Ventilator, die Frischluft durch das Gebäude zu pumpen, weil der Ventilatorstrom das ist, was viel Energie braucht. So we developed this idea of integrating the shafts, all the air going just upwards. So if it's warmer than outside, it goes on its own. Size the shaft to low speed, low pressure drops. Then had the problem of heat recovery. So we put a little heat exchanger on top here. So it's an air to water heat exchanger. We extract the heat from the exhaust air and pump it with the fluid system back to the basement. Have another system like this, and then preheat the incoming air. So we don't bring the air back because that needs large shafts. We just use some water pipes to bring the heat back. Then we have a earth duct in the ground to precondition the air. We have a little heat exchanger connected to the district heating system, and that's about it. So we don't have any mechanical cooling there. The building slabs are integrated with the radiant fluid systems that uses groundwater to cool and a district heat to heat them. And we have a open cooling tower on the roof that just provides evaporative cooling at night. So that is the whole system. And in the offices, it's really ducted through a raised floor, open, no ductwork, to really bring comfortable air into each office space. And people don't even know that they don't have a fan running this, because it's supplying fresh air. And on the lower right, you see the earth duct. This is like a 130-meter long channel in the ground, 3 meters by 5 meters, to use natural cooling and natural preheating to provide air. The question of the client was, will that work? Only natural forces. So we had to run a couple of complex simulations for shafts and offices and facades to show that it works. And then the mechanical engineers came in and said, but we need an exhaust air system on top of the roof with filters and all of that, like a big box. And we said, no, we don't think we need that. And then we had to prove that we never get wind in that exhaust shaft to actually stop the system from working. So we did a couple of airflow analysis by computational fluid dynamic programs, and showed that we always, on top of that chimney, have negative pressure, and actually convinced the client to leave out that system. And the mechanical engineer complained, but in the end, they agreed. So we don't have a fan there. We have a little fan in the basement to pump the air through in summer, but that's about it. And that is how the air enters the room. It's like a trickle vent, displacement ventilation, low airspeed into the room, connected with a heating convector to heat the facade. That's about it. That is the return air system, also developed sound dampening devices that have low pressure drop together with companies. So it's all custom made for this task to run naturally. The interior design can be questioned. That was done by the Munich Ray team. So we're not responsible for this. But the exterior, that facade provides a lot of solar protection, good daylight, and the ability to natural ventilate. And the inherent system reduces the carbon emissions of that building by 2/3 almost. And that is about the equivalent of CO2 substitution of the whole BMW PV roof with 800 kV installed power. So doing that building conventional would have emitted way more CO2, and that was 20 years back. So that system is still on the very efficient range compared to buildings that are developed today. That was the excursion to the past. And then we did something right next door, across the street for the Deutsche Alpenverein. That is a renovated building of an existing building, just stripped off the facade and all the interiors, just using the structure, adding a new facade and adding a simple system that can now directly, low-techly ventilate through the facade and provide comfort without all these installations. And you see this building is right in front of a big high-rise from Helmut Jahn, 130 meters high, and we have strong winds around that low-rise building. That is the entrance area with a large atrium, and then all the offices are the two sides there. So what we did is we just integrated a trickle vent in the facade, a simple akustischer Dauerlüfter, and that is where the air comes in. And that acoustic dampening is needed because it's right at the highway entering Munich from the north. So it's very loud. So we need this acoustic dampening. That's a Dutch system simply to be implemented into facades. We implemented it into the spandrel panel at the Brüstung. And then we added a heat exchanger for heating here. So that fresh air comes in, is preheated here, and then enters the room. So we have comfort ventilation without a big system. And interiorly, that is like this box where it's all integrated all along the facade. And that's about it. That's all the ventilation you have. Nothing, no ductwork at the ceiling. Ceilings are just the concrete ceilings stripped off the suspended ceilings they had before, some acoustic elements. And you see these ceiling fans. They are for summer comfort enhancement. And I'll show that later. And a view that's all open office space, equipped with a lot of people. We tour clients there. It's the biggest example of low-tech functional architecture for office space that we have. So that's all they have, and they feel fine. And all the clients that we tour there are pretty convinced of that concept. So in summer, normally you just cool the air to 24, 25, and then you feel comfortable. If you don't want this, because you don't want that much of air conditioning, you can also use like a little fan to just move the air and create this cool breeze, a kühle Brise that allows you to be comfortable at 29 degrees, just as 25 before. So same comfort feeling. And this is the science for that. This is the ASHRAE calculator of thermal comfort. And you have to be in that blue range down here. And at 24 degrees with non-moving air, you're right in the center of comfort. It's all perfect. Summer comfort is fine. If you're at 28 degrees and move the air by 0.8 meters per second, about this much, you feel the same, although you have 4 degrees more in the room. So that principle allows us to reduce the amount of air conditioning because people feel the same and you don't need to cool the space just as before. And then, surprise, surprise, that kühle Brise effect made it even into German codes. So in the German code for thermal comfort, at indoor temperatures above 25 degrees, we can subtract 1 to 2 degrees internal temperature in comfort sensation if we are able to individually move the air. So you either open 2 windows like here and there and have this breeze in summer and you feel fine, or you start this fan. But not below 25, then it's draft, and not just dictated. So you need to have individual control over this fan. Then you're allowed to do that. So if you run a simulation, look at the performance of an office room and put the indoor temperatures here and the outdoor temperatures there, and you have 1 year in one graph, pretty nice. So you see left down here, this is heating mode. At -10, it's 20 degrees inside, 21, fine. And then at the very end, on the other side, it's 36 degrees, and you get like 29, almost 30 degrees indoor. That's just passive night ventilation and a heating convector. So if you now integrate a ceiling fan, this is what happens. So you're almost completely in the comfort range just by adding a fan. So no air conditioning, no active cooling, same room, feeling comfortable and not feeling as hot as this one. Although it's still 29 degrees, it just feels like 26. So that is the similar effect of if you have an active cooling in the slab, where you need to put energy in to cool. Similar, slightly better curve. If you have ceiling panels, if those things will be activated, then this will be the performance. So it's replacing cooling by air movement is the simple idea. And you can have these fans in all shapes and forms and all types of office, residential, whatever environments. And they just move silently, slow, provide this airstream, and you're fine. So that's what they do at the Deutsche Alpenverein. And now we exported this idea to Austria, and together with Volker and Gilbert and Peter, we won the competition for the Tiroler Fachberufsschule für Fotografie, Optik and Hörgeräteakustik. So photography, optics, and sound engineering, like in Hall in Tirol, pretty close here, finished this year, almost finished. And this is the extension of an existing school, only 700 square meters in a completely timber building with 11 classrooms and a teacher's room. And we adapted this concept from the Deutsche Alpenverein to the school building. So a similar system here at the facade. Then we have the overflow into that corridor space with sound dampers and fire dampers. And then we have this simple axial fan up at the roof and a damper to just provide constant airflow. And we integrated these ceiling fans. And that principle of preheating the air was also exported here. And as you can see, made somewhat slimmer than in the Alpenverein. This is the ceiling with acoustic functions and the ceiling fan and some data support. This is the timber structure with the open slots here to bring these trickle vents in. So they go just into the facade. And then you bring that finished element and you have a slim balustrade like this that does ventilation and heating for all the space. And that is the other side. So the exhaust goes into that staircase, is lifted up to the very top, and there we exhaust the air. And they wouldn't really believe that this is working. So we started something together with Dominic and one of my colleagues, Martin. We actually built such a thing and tested it because that functionality we could have done like airflow calculations and then we get colorful pictures, but we never really convinced people with that. It's just, they want to see something with their eyes. So we said, why not test this, build it like in simple wooden timber construction. And then we just took some, now I need to find my mouse here somewhere. You see it? Ah, here we go. So we started the system. So we have a hot convector and we put some smoke in so you can see how the air flows. So there's a supply air is coming from outside. It's going down. And then coming under that slab into that heating convector, and the room air is coming, mixing with the supply air, and then being lifted up. And so we get warm air into the room. And here the room air is taken in to actually make that thing work. And the mechanical engineers said, this is all okay, but what happens if, for whatever reason, this convector is not switched on, but off? And then it will freeze and break, and we have a problem. So we said, we do another movie, and we did. And we found out if we don't switch the convector on, the air is just coming out at the bottom, doesn't harm the convector, everything's fine, inherent frost protection, with no control element needed. And they believed us and said, fine. But then still, the question was, if we would do a mechanical system with heat recovery, wouldn't that be better? So we had to compare that scenario with what we proposed. And we found out, of course, with the heat recovery, you use significantly less heat, but you need more fan power to drive the system. That is the yellow bar of electricity. If you take the electricity carbon emissions of the Austrian grid, you can't see it, it's down here. And the district heat performance of the T-gas Fernwärme Hall, you find out that in carbon emissions, that penalty by using more electricity is outperforming that savings in heat. And we use more carbon in this scenario than in the scenario we had. And that scenario was way cheaper. So that all big system, and we didn't have a box on the roof. So being so much cheaper, it more or less paid for that whole PV area on the roof that is going to come there in hopefully a couple of months, weeks, hopefully. It has been ordered, it's paid for. With that performance and the low-tech system, we generate, with the electricity that we generate over the year, twice as much carbon savings as the building will need. So it will be climate positive in operation, and we have that budget over a certain amount of time to actually even compensate the embodied carbon, the graue Energie of the construction, which is not that much because that building is made completely out of timber and therefore has a pretty low carbon footprint. Talking about building construction materials, this is a project that we did for Ricola Kräuter bonbons in Switzerland with Herzog de Meuron. And it's a building made out of rammed earth, Stampflehm, finished 2014. So the purpose of that building is to store these herbs. And these herbs are sensitive not only to temperature, even less to temperature than to humidity. Relative humidity is what counts. So their whole process should be housed in a new building. And the idea was to use a building made out of rammed earth to do that. And that's what we got in the end. So you see a large wall out of earth that is from the site more or less 10 kilometers around, and generated on site. So it's like the herb storage to the right, and then manufacturing and some people and some offices on the left-hand side. And then we looked at what is the humidity levels. They only want to keep 10 degrees inside that storage space. But what they don't want is large swings of relative humidity, because that is killing the herbs. So we, if you look into the code, what to do, thermal insulation, you need a U value, U-wert from 0.5 watts per square meter in Kelvin. That will be a sandwich panel, insulated steel, no humidity absorption. So if you run that in a combined humidity and temperature software, you find temperatures quite okay, but relative humidity from 30% to over 90% over the year, large swings. If you replace this wall by rammed earth, this is what you get. You get almost 1/3 of the bandwidth of relative humidity swings. So it's absorbing humidity, bringing it back into the air volume. So way better in terms of keeping humidity at the right level. But thermal insulation is 3 times worse than the sandwich panel. So now the question was how to get this through the Swiss code of thermal insulation. And for that, we did this graph and said, a rammed earth building, you do it locally and it stays there almost forever. We said only 100 years. And then we look at the other facade alternatives, sandwich panel or sandstone, and they would have to be replaced every 25 to 30 years. And if you look on all that embodied carbon needed to replace these walls, you get the step curves here. But what you see here during operation, this is much lower in inclination than this. So this uses more heating energy, but stays there. The other one uses way less, but needs to be replaced. And the total 100 years performance were way better than the other alternatives. And that way, in Switzerland, the authority said, okay, you can do that building without insulating it. And then this is just the ingredients of the walls. They come all from local 10-kilometer distance. This is the weathering of a rammed earth facade. So here's the west facade with all the wind and water on. The south facade doesn't have that. This is how you construct these things. Each element is about 4 to 5 tons heavy. And it doesn't have any reinforcement. So you need round windows because you don't have reinforcement to hold the window up. And then it's like a brick construction. You just use mortar to, and it was done in 3 months. The window details, so like self-supporting window. And then you fill the gaps in order to make it at least airtight, which is what we did. And you get this large box with all that capacity for absorbing humidity. Bring the herbs in, process them there, store them there, and have a wonderful, nice building with an integrated high performance, not in all details. And now transferring the problems, I talked about Asia, into hot and humid climates. So this is a school in Singapore we did together with Siri Multiply Architects from London and Singapore. It's the School of Design of the University of Singapore, and it's their 4th building. It's a new one. So the idea was to actually do a building that is different from standard buildings in the tropics, what I showed before. So no block, no sealed facade, but an open building, cross ventilation, stacked planes, shading and ventilation, a large roof that shades the whole structure, equip the roof with PV, and generate electricity. Use that approach from the Alpenverein, and it actually, this building was finished before the Alpenverein was finished. So we exported that idea back to Europe and not from Europe. And then created different zones of hybrid ventilation, air conditioning, certain elements there, and naturally ventilated spaces under that canopy roof. We ran all that in thermal simulation, provided a minimum amount of fresh air that was dehumidified, so like slightly bringing humidity levels down, and then having the ability to operate windows. And this is how students work in there, and that's at 29 to 30 degrees. But with all these fans running here, it's comfortable. They even wear sweaters there, or just sit in a productive working environment. Then you have the lecture halls directly next to it. You have outdoor spaces, shaded, in the outside, humid, a lot of radiation, and you have all these nice breakout spaces in the open, other way around. And then this large canopy that shades it all, that provides these terraces stacked on top of each other. And then on the top, it's all equipped with PV panels. And the roof, you know, so much PV as we could possibly get on there. And that is the whole story. So with that given size of a roof, we could generate 500 megawatt hours of electricity over a year. So we said, that's the budget. If you do a standard building in the tropics, it would consume 4 times as much. Same floor plates. Optimizing the envelope and the system would bring you down to 1200, way above 500. So we needed this hybrid approach of cross ventilation and just no air conditioning or less air conditioning and air movement. We needed optimized design of the facade and looked pretty much in detail. And we said, okay, we can make it. If everything in design is transferred into reality, the budget of the PV will be okay to run the building without any external energy. And then we measured for a year and found out the building roof generated 28% more than the building needed. So proven climate positive, we extract or carbon dioxide from the atmosphere. So summing up, even in the tropics, with that approach of a different way of creating comfort, air conditioning needs are cut in half, and then renewable energy is capable of doing the whole job. So that is net zero energy, or even positive, 100% done on site. And then we said, okay, this is a new building. So we forgot about all the concrete, and you've seen the amounts of concrete that go in a building in Singapore. And they also had next to that School of Designs 1 and 3. Existing buildings on site. And these hidden treasures were in a shape you'll see in a minute where you wouldn't believe that. So that is like the space for the students there. And that's what it should be. That is the facade. And that's what it could be. So we found this. I just want to be 1,000,000 miles away from here. And just remember that picture. It'll come back up again. So this is the environment, no daylight, no view to the exterior, bad air quality, no comfort, horrible. And then having a building next door that is completely different. And this is the facade. So no daylight, you can't look out. Artificial lighting is running all day. And then we looked at the structure and found this. So this is the studio space. And these are the suspended ceiling with mechanical equipment inside. And a large floor plate, no daylight. So we said, why not cut an atrium inside, remove all that, and then just look what we can do with the space, do a new facade and try it. So this is what we did. So this is like taking out what was there and looking at the existing structure, redoing it. Here, there. There was so much space in that building that was occupied by ductwork and mechanical equipment or just left empty. And then we did a daylight simulation showing this is the existing situation. It's dark, even if through the facade light would come in. And then if we cut that atrium, it would turn into this. So we said there is potential of keeping the structure and doing something that is really nice. So we ran some daylight simulation. That was before, that is after. That's like it's 3 times as much daylight inside the space after that renovation. New facade, removing all the structure. And then we looked on, you know, what is the budget of material in that building? Slabs, columns, and we did a little breakdown, you know, foundations, columns, beams, slabs, walls, and this is what we kept. Some of the slabs we had to take out for the atrium, the facades went, the shading went, and then, you know, cutting holes in there in the existing structure, quite a challenge. Then looking on the conditioning concept, it was all air conditioned, but the system was in such a bad shape, it didn't provide any quality. So no daylight, no natural ventilation, full air conditioning, but not really working. So we did that cross ventilation approach of the new building. We put daylight in, and we had some spillover spaces. So spaces are connected now. And this is what it is. So that's all the left over from the mechanical system. That's supply air. That's it. Not more. Everything is open. We've got these ceiling fans in white this time. We got a different facade. We get light in. We just left the floors. And that space will turn into the right space. So now the guy came back. So it's not only new construction, you can do things to old construction that really work. And now going to the from the extreme warm to the extreme cold climates, this is a net zero carbon complex at the University of Calgary in Alberta in Canada, Western Canada, done with Dialogue Architects, finished 2019. The tower was 2019. The block there on the right-hand side was finished more or less last year. So that was what we found. It's a library tower and this block building. Same story, different climate, no daylight, a lot of concrete, poor performance, heat losses forever, thermal bridging all over the place. And we said, well, you know, either tear the whole thing down or look at the structure, what it could be. So we stripped the facade elements, found that structural core, left it, preserved it, and wrapped a glass facade around it completely once around the building. So it's a warm jacket around an existing building structure. And why warm? It's super cold in Calgary. It goes down to -30 over months. And then there's a short summer. It goes up to above 30 for weeks. And then there's some intermediate season where you can naturally ventilate because it's mild. But even in summer, large swings from day to night. 15 degrees colder at night, so 20 degrees at night and 35 in the day. And then we see solar radiation on a southeast facing facade. It's perfect for passive preheating of a building. And we said, okay, then we stripped the structure as in Singapore. So that's the leftover of the concrete structure. No suspended ceiling anymore. Instead, we put a raised floor in to bring the supply air in at low speed at the facade perimeter. We put a triple glass facade to the outside. We have these columns there, and then just a single glazing to discouple the shading from the interior space. And then we looked at, this is the core elevators, and then this is all around the office space, the existing columns. We created this double facade corridor once around. These are the heating and cooling panels, and that way we can actually use the structure. And with that efficient facade, we would prevent overheating, especially in winter and colder seasons when the sun angle is low. These, on the lower hand, you see it, these single facades with interior shading absorb so much heat that it's overheating at -10. It is 26 in the room. At -0, it's already 28. And if you try to cool that, you use a lot of cooling energy just to provide, to overcome the poor performance of that facade. And in the double facade, you don't really need that cooling because the facade does it all. So in the finished building, this is what you then get: an interior single glass facade with operable elements, and then an exterior fully controlled facade that does all the job of creating a buffer zone once around the building. So the question was how to control that. We have a couple of examples also in Canada, Manitoba Hydro and Rosenheim, and in Frankfurt, where we done similar things. So we started to look at the wind pattern in Calgary, and this is, the arrow shows the direction of the wind, the size of the arrow shows the speed, and the color shows the temperature. And what you see is chaos. And a good friend of mine, engineer from Calgary, said, in Calgary, it's easy. If you don't like the weather, you just wait 15 minutes and it changes. And it does. So for a facade system to control that, quite a challenge. So strong fluctuations in everything. So we built this model again, once around the building, facade, interior, shafts, natural elements. and started to derive an optimal control strategy for all the flaps around the buildings. And then to all the 4 orientations, we got graphs like this. And this is the temperature range that this buffer zone now has. And if you integrate that and order it by magnitude, you get these curves. And these curves are ambient temperature, peak summer, peak winter, and that is the facade temperatures all around the building. And we wanted them to be in a range from 10 to 25 degrees to be able to always open a window without being too cold or too hot. And you see 90-something% of the time that works. So that idea provides that warm jacket and a buffer zone that provides comfort for people and allows you to naturally ventilate the overheating hours off without having to cool. And then we tested it. So these are the operable elements. And now you need to actually control them in a way that they always do the right thing. And then we measured that. And this is facade temperature, south and west, over a full period of like a month, almost a month. And you see that is the temperature scale, and it goes down to -30 there. And even at -30, the facade temperatures is about 7-8 degrees. So we got it into that band almost. So we were surprised ourselves that it worked that well. We had to, arrange a couple of things in the controls, but essentially the system was operating fine, and we actually get this capability of natural ventilation. And then the corner detail is a bit created a problem for the facade manufacturer, and these operable elements need to be controlled smoothly. And this is the before-after picture. So they extended it by 3 floors. We got this new tower now. And that is the carbon balance, having data for the tower, but a projection for the block. So it's like half-half. I mean, it's a harsh climate. And with the PV systems we have on the roofs of all buildings and integrated into the facade of the block, we can do 50% on site. So this is now the state of last year when this block building was also finished. And there we have a facade, also a double facade with integrated PV panels. That's the other side of the thing, creating like a wrapped round double facade around the study rooms. And here you see the integration of photovoltaic cells in the outer facade of that block. And the nice study areas that are created by these light shafts going once through the building and into all directions. A lot of quality there that they didn't have on campus before. And this is what actually helps to bring the carbon balance in. And what you also see here is this is all supposed to be PV. It's coming. The structure is up there, and they're gonna bring the panels on pretty soon. So this is now shifting back to Germany, but from office buildings or study buildings into production. So that is a production hall for Elobau Werkzeugbau in Thüringen, in Probstzella. And it was done with F64 architects, and the client said, this is going to be carbon neutral. I just want to know how, not if. And all their buildings are that. So we have a large spans, wooden construction, column 3. From the top view, the whole roof is equipped with PV modules. And there's a production line inside. So we needed some external space to actually provide more PV to overcome the production requirements in electricity. So in the end, we have twice as much PV. And that about does the job for being carbon neutral. We have electrical storage batteries to decouple that building from the grid. So if we have surplus on the roof, we can put it into the battery and take it out, but not on a seasonal scale, more on a daily scale. These batteries are expensive, but they are not in the basement. This is like a corner of the entrance hall. So they're displayed to people. This is what is helping to overcome the budget. And if you do the math and all that balancing, you find a carbon balance of minus 62 tons per year. So much overproduction of the PV over the demand of the building. And as this was small, we then were commissioned to do a master plan together with OMA and 3XN, the two winners of the master plan competition for BMW, to convert their urban production right in the center of Munich into a green production field. So master plan for that. We worked on this, and this is how the Stammwerk is today. You see a lot of factory, almost no green. There are 1,000 trucks entering and leaving every day. So it's really an operating facility, and it's producing combustion engines today. The conversion is they want to do just electric vehicles here. So they want to replace like half of that stuff with new factory halls for electric cars. And this is what the master plan proposes, a combination of PV energy generation on the roofs and intensive green, not only on certain roofs, but also in that spine for people entering the factory. And if you look at ambient outdoor comfort today, if you enter the BMW production site, it's getting hot, like in a city. And we want to reverse that, so it's more like the park right next door. This is the Olympic Park to the left here. And then they told us, well, we want to get carbon neutral. And we said, fine, we can calculate how much all your roofs would contribute. And that is the number, 5% of what they need. So we told them, you need more. You need more, you need windmills. And that was just a graphic from OMA. It's not supposed to be right next to in the city. But we said it should be linked to the factory. So at least they should be visible from the factory roof. So not somewhere, but in close vicinity. And that's what the vision of that is, to actually provide a green factory in the center of a city. So that balance of carbon neutrality can be done in 3 steps. First step is just building operations, heating, cooling, ventilation, and lighting, and some pumps. You need a certain amount of PV to compensate that, to come to net zero. Then you include the user, and in terms of the factory, it was large machinery. So you need way more. And then you can include construction material, and you need even more. So with all of that, people in Germany say, well, I don't want to see windmills. I don't want to see PV in the green. And we told them, this is right where I live. This is like, everything is less than 5 kilometers away from where I live. And we have to actually learn to live with those pictures, that we have windmills in front of the Alps, that we have PV systems on right next to the woods. And you know, there's sound from windmills, but they're right next to the highway. The highway is much louder. And to see that PV field from the highway is quite tough. But this is like what you should do. New systems, directly relate them to your building, and then it's an honest balance. So just go back from the large to the very small. This is a desert house in Spain. We did together with Office from Ljubljana, finished in 2018. And unfortunately, it's not there anymore. It's in next to Granada. Desert climate, -5 to up to almost 40, even more than 40 probably. So we looked on what can we do to actually survive in a small house in the desert. And the answer was this: overarching roofs, a lot of shading, fully glass building, triple glazing, selective coatings, some exterior shading, and I have to state they don't work. They are not resisting the wind. And then a small footprint, 20 square meters only. You sleep here, you shower there, you eat there. No, it's the other way around. And in the center, there's 1 square meter of bathroom. This is all what we have on the roof. just these 3x4 panels. And this was the climate concept. It was like a reversible heat pump to heat the thing and cool it out of solar energy. And that was about it. And have these overhangs to shield ourselves from the sun. This is all the mechanical room is. It's just in the sink, below the sink. Electric batteries and a couple of converters. And then that system on the roof. And you're out there in the desert with a magnificent view. And you have sliding doors, so you can adapt from inside to outside pretty fast. The shower, the bed, and the breakfast area. I'm standing in the shower. That's, yeah. And at night, it was magnificent. So we traveled there, my wife and I, and that was our car. We had to park it. And then you get there, and then you sit there, and it's 100% renewable energy, and it's off-grid. It's just relying on the batteries. So even in the desert, you can do it. So why not do it in other areas too? So now coming from the building side, and I don't know how much I can use in time, but that is really important because it's interesting stuff. So that's outdoor comfort. And this is like the typical patio in a in southern areas. So why are we doing this? We want to get into the no thermal stress area sitting outside from the hot or the cold, doesn't matter. We have to have all these parameters under control. So shading, air velocity, temperature, sky temperature, solar radiation, wind, all of that. And bring that into a scale where we can say it's comfortable, and that's the green and yellow. And when it's getting too cold, it's blue. And when it's getting too hot, it's red. And when it's dark red, it's really hot. So that is like where you want to be in warm and humid climates. And then we tested it at the Austrian Pavilion on the Expo in Milan 2015, together with Austrian architects. And the idea was to actually get this, like a wood forest in the hot climate of Milan. And somehow we as climate engineers had to enhance the feeling of the wood a bit because it was a very small wood. And there's one effect that's really important. That's like they had these membrane roofs over all the access areas. And a membrane roof shades you from the sun, but it gets hot itself. It gets up to 40 degrees, and then it's like a heating system above you. So it doesn't really feel comfortable. If you have a tree in the same sun, it's only 30 degrees. So that feels much cooler just because it's a volumetric thing that has some evaporation and not just one single fabric. So that is the first thing. The next thing is at walls, the same effect is there. If you have a green wall, it's much cooler in the sun than a normal wall. So the idea of that pavilion was to leave the roof out, create this forest, leave the rest of the roof for PV panels to power the whole thing, and then you use the evaporative cooling effect of trees, slightly enhanced by machinery, to provide this good comfort. And then you had to wait in line in the sun outside to be left in. And inside it was cool, a breeze was there. And that was just evaporation of water and this moving airstreams. And our measurements showed out here, you are in the dark red, getting into the shade next to the forest. It was almost comfortable. And then where you had these fans blowing at you, it was 6-8 degrees cooler. So people really noticed that. And we had these fans with humidifiers everywhere, hanging in the trees. And then we said, well, if we can do it in Milan, maybe we can also do it in Singapore, doing something to the outdoor experience. In a park in Singapore where it's humid, and we said evaporation in a humid climate, does that work? So we did the same thing as in Milan and did that under a bridge, on a bridge under the trees. And people's response was the same as in Milan. They loved it. And here's a little, where are we? Movie. showing this. We just put up the system, put up some cameras, and walked away. And then people didn't know what was happening. They are in that park, they cross this bridge, they find these systems, which are Dyson fans without a blade. And it's actually cool. I mean, in a double sense. And it's high pressure evaporation. Two advantages. One is what you just saw. You don't get wet. It's immediately evaporating. It's just cool air. You can put your cell phone in front of it. It doesn't get wet. And the second thing is it doesn't use a lot of water because it just used the water to evaporate and not to spray you and you get wet. So it was, that was fun. That was convincing people because it's really something that with a low effort can provide comfort. And then we were called by Voha, the architects from Singapore we're working a lot with, for another pavilion, Expo 2020 in Dubai, so even warmer. And they said, can we do the same? Can we provide a pavilion that is green and cool? And can we do on the footprint in that period where it also goes up to almost 40 degrees? It's winter, but the shoulder season was quite harsh. And then they said, not only the solar canopy to provide all the energy, but also provide the water that pavilion uses by solar desalination in that climate. And then create this path that leads you through this pavilion. So an idea of an open forest with cones of open areas, and you always have these features where it's getting cooler. And then we have energy for solar desalination and provide fresh water from the salt water of the sea and provide enough to run the whole pavilion. And then that outdoor comfort experience is you're out in the hot, you arrive there in the shade, you get into the pavilion, and it's getting cooler and cooler. So out there, it's, you know, red is dominant. And then you get inside, it's getting better. You get more to the greener areas inside, and in the deep shades, it's getting better. And even outside with the dry mist, it's completely comfortable. So that was, they never learned. The exterior was done the same in Dubai as in Milan, and that doesn't work. It's not providing enough shading. It's super hot, but they kind of did it no matter what. And then people were in line in front of that pavilion again, waiting at the entrance. And then you get into the same experience as before. And it's not that we just do the design. We also have to send people, and this is Martin, he was on the mock-up on the other thing, to really make these systems work and check their performance by measuring the effects. And then all the green on the buildings was in little pots watered by the desalinated water. So it provides that. Maybe I can run that. Oh, maybe just like this. So this is a shot in the outdoors, 40 degrees temperature, surface temperatures. And now he's swinging into where the dark, deep green is on the pavilion, and it's 24. So that temperature that radiates at you outside is super hot and inside is cool just by evaporative cooling by the plants themselves without our system. And then on top, you get these fans. And same thing. You notice the difference immediately. You see these pots where the plants are in, and then all this sophisticated watering system to actually keep them green. And now we actually transfer that back into something that is more related to buildings. This is outdoor comfort in India, in Hyderabad, for a campus we did together with Morphogenesis architects for Wipro. That's a software company in India. In Hyderabad, it's super sunny, twice as much as here. Gets up to 40 degrees. It's got a monsoon season. It's hot and humid, and it's dry and hot, and it's got different seasons. Warm and dry, dry and hot, warm and humid. And the idea was to do a restaurant in the center of that block in the outdoors. So you would eat your lunch every day of the year outside under a canopy, which is providing shading together with the buildings right next to it. That's the entrance. So we actually designed the whole courtyard in a way that the prevailing winds would go through. So you would always sit in a breeze. And then we designed these systems and showed them to the client. And this is actually in India. We brought one of these fans on the plane, put it up there. That's their outdoor restaurant. That's like in 30+ degrees. And the client was skeptical. And then after a while, they said, okay, I think we can do that. This is quite comfortable here. And we actually convinced Hari, who's the boss of that whole thing, to do the 5,000 square meter restaurant outside and not build an inside restaurant. And he said, you have to provide that this works, and then we do it. And then we started in a 500 square meter testing restaurant, which is already there, and equipped it with fans. And that's like the adjacent building, much smaller, with the same idea of the roof, and these outdoor tables. And they are eating there now in the much cooler surroundings than before. So that was it. Thanks a lot.
Thank you. That was amazing and inspiring. It's Fragen.
And long.
That's okay. When it's inspiring, it's okay. Wir brauchen, glaube ich, das Mikro nicht, oder?
Nee, jetzt nicht mehr.
Und du hast es eben so.
So wirklich nah dran. Ja, dahin.
Die Hochrechnung des Energiebedarfs, auch mal das Vergleichen, die bei dem Beispiel der Gebäude war, welche Energien waren da immer mit einbezogen, also auch als eine Hochrechnung auf die Lebensdauer des Gebäudes?
Nein, das nicht. Das war bisher, also die Sachen, die ich gezeigt habe, waren immer nur praktisch Operational Energy, also Betriebsenergie pro Jahr. Aber da alles, also der Nutzer, alle Geräte, alles, immer mit den CO2-Faktoren. Und dann gibt es dieses Thema graue Energie. Das haben wir auch gemacht für das Gebäude in Singapur, wo man sehen kann, wie viel haben wir denn gespart, dadurch, dass wir keinen Neubau machen. Und das ist ein Budget, da braucht man auch bei einem schlechten Gebäude einige Jahre, um all den Stahl und den Beton zu kompensieren. Das heißt, wir sehen jetzt, wir machen solche Vergleiche, hatte ich jetzt nicht dabei, aber machen wir, wo man sagt, man braucht Einsparungen von einigen Jahren, auch um effizient gebaute Gebäude praktisch den CO2-Inhalt der gebauten Struktur wieder reinzuholen. Bei PV-Modulen wird häufig die Frage gestellt, wie lange dauert es, bis die sich amortisieren? Sage ich immer, hängt davon ab, wo sie stehen. Entweder in Indien, doppelte Sonne wie bei uns oder bei uns. Aber selbst bei uns sind es nur noch Monate bis 1-2 Jahre, bis sie sich quasi amortisiert haben und dann nur noch beitragen für das Haus. In wärmeren Regionen geht das noch schneller. Und der Energieinhalt und damit auch der CO2-Fußabdruck von Solarpanelen, der ist um einen Faktor 4 gesunken in den letzten 5-6 Jahren. Also das, was in der Datenbank ist für Bewertung von grauer Energie, sind so 7-8 Jahre alte Daten, die sind wesentlich höher als das, was man heute kaufen kann. Und es gibt diese European Product Declarations, EPDs, wo drin steht, wie viel CO2-Emissionen hat das Produkt gebraucht, um es zu erzeugen. Das gibt es nicht für alles, aber das gibt es für immer mehr und mehr. Und das wird mittlerweile auch ein Kriterium, dass das angesetzt werden kann, um in solche Berechnungen einzufließen. Also das heißt, das ist etwas, was schon bewertet wird. Wir haben eine Fassadensanierung gemacht in Bremen für einen Turm von Helmut Jahn, wo das außenliegende Sonnenschutz kaputt gegangen ist, der Wind zu stark war. Und dann war die Frage, bauen wir eine neue Fassade und machen einen neuen außenliegenden Sonnenschutz oder machen wir das cleverste innenliegende Sonnenschutzsystem, das uns eingefallen ist. Und wir haben das ausgerechnet, was wir da mehr verbrauchen und haben das dann über die Lebensdauer von der Fassade gerechnet und gesagt, es lohnt sich nicht, eine neue Fassade zu bauen, weil man es nicht, das, was man jetzt ausgibt, nicht mehr einspart über die Lebensdauer. Das heißt, wir werden diese Betrachtung ändern müssen, auch mit Blick auf die Klimakrise, dass wir sagen, wir können eigentlich nur noch die Dinge ersetzen, die wirklich sich effizient herstellen lassen. Und wenn man viel Beton, Stahl und Emissionen braucht, dann muss man sich wirklich fragen, ob man das machen will. Und das ist, glaube ich, auch die Diskussion Hightech, Low-Tech, wo man sagt, wenn ich das ganze Equipment nicht brauche, dann brauche ich auch weniger graue Energie, um es herzustellen. Und damit bin ich schneller in der Amortisationsphase, als wenn ich sehr viel Aufwand einsetze. Und die ganze Frage, ob man jetzt Betonstrukturen baut, die stark auskragen, die solche Transfer-Slabs brauchen, ist eine, die man stellen kann. Aber eine, die uns ganz häufig gestellt wird, ist es besser, in Holz zu bauen als in Beton. Klar, Holz hat wesentlich weniger CO2-Inhalt als Beton. Aber man vergleicht nicht Äpfel mit Äpfeln, sondern meistens Äpfel mit Birnen. Also ein Holzgebäude hat einen Stützenabstand von 5,50 Meter, 6 Metern. Dann funktioniert die Holzdecke. Ein Betongebäude hat 8,50 Meter standardmäßig. Wenn ich 8,50 Meter überspannen will, brauche ich eine 30er Decke oder 28, was auch immer. Wenn ich jetzt aber auch nur 5,50 Meter überspannen würde mit Beton, dann käme ich mit 20 Zentimeter Decke hin. Also ich hätte schon ein Drittel gespart. Das heißt, wenn man wirklich die Sachen miteinander vergleicht, braucht man ein bisschen mehr als nur den Energieinhalt der Materialien. Man braucht eine Tragwerksplanung, eine sinnvolle Optimierung des Gesamtsystems und dann kann man es entscheiden. Und das machen wir mittlerweile mehr und mehr, aber noch nicht so lange. Ich habe das vor 4, 5 Jahren immer noch abgelehnt, das überhaupt zu machen, weil die Daten in den Datenbanken so schlecht waren, dass ich gesagt habe, ich kann nicht als Berater auftreten und ich weiß selbst nicht, ob es positiv oder negativ ist. Da muss ich schon ein bisschen bessere Daten haben. Mittlerweile ist das besser geworden und wir machen das auch sehr grob, weil ich glaube, die detaillierten Betrachtungen, die auch in Zertifizierung eingehen, ich glaube da immer noch nicht dran, dass das alles stimmt, weil das ist wirklich ein Riesendatenhaufen, den man da verwalten muss. Und das geht alles langsam. Das heißt, die Sachen, die man heute kauft und verbaut, die sind nicht drin in den Datenbanken. Und deswegen ist dieser ganze Aufwand manchmal ein bisschen fraglich. Lange Antwort auf eine kurze Frage.
Wir sind ganz am Anfang mit Ihnen angesprochen haben, Vergleich zwischen Leute und wie sehr sehen Sie da diesbezüglich Potenzial von reinen Gebäuden, zum Beispiel 20 Münzenach, oder auch zu monolithische Bauten, das rein Holz oder rein.
Also das haben wir untersucht. Genau, wir haben das untersucht, also jetzt für einen Wohnbau mit Florian Nagler zusammen. Das war so ein Programm, das hieß einfach bauen. Und das meinte nicht einfach mal losbauen, sondern einfacher bauen. Und da haben wir verglichen monolithischen Beton, Dämmbeton, Ziegel, Holz für ein Wohngebäude, 3 Geschosse, identische Gebäude, gerechnet, optimiert, alle Parameter angeschaut. Und um es kurz zu machen, das Ergebnis war, der Baustoff selber ist es gar nicht. Es ist, was die Nutzer damit machen. Wesentlich mehr Einfluss. Und auch gegenüber einem Passivhaus oder einem Zero-Energy-Gebäude, wenn man es falsch benutzt, ist das der Haupteffekt. Ich glaube schon, dass dieser Low-Tech-Gedanke mehr und mehr kommen wird, einfach weil das Material knapp ist. Man muss jetzt ein bisschen gucken, manchmal ist Low-Tech einfach nur Dinge weglassen und es funktioniert okay, aber nicht für alle Anwendungen. Also auch 22, 26 funktioniert nicht für alle Anwendungen, aber für das, was da steht, funktioniert es schon. Und dann werden wir einfach überlegen müssen, was können wir uns noch leisten, was brauchen wir überhaupt? Und ich glaube, die Frage nach Robustheit von Gebäuden und nach Suffizienz, also was brauchen wir wirklich, die wird es dann ein Stück weit entscheiden. Und meine Meinung ist, es wird in die Richtung weniger Technik, weniger Aufwand gehen. Und dann gibt es noch einen Faktor, den habe ich ganz am Anfang gezeigt. Und man kann sich das auch in den Wetterdaten anschauen. Es wird wärmer werden und es wird weniger lang und weniger kalt werden. Das heißt, diese ganze Dämmdiskussion wird noch weniger relevant, wenn man es praktisch mit dem Wetter von 10 Jahren anguckt, dann wird man sehen, wahrscheinlich werden uns irgendwann wieder 8 cm Dämmung reichen. Wir brauchen keine 18 oder 22. Und dann kann man auch darüber nachdenken, ob man das nicht in Holz oder in Ziegel oder in Beton auch realisiert. Und es ist auch eine Frage, welche Materialien sind verfügbar. Also, weil neben der Energie haben wir auch eine Materialkrise. Sand ist knapp, Stahl ist knapp, Beton ist nicht beliebig viel herstellbar. Also wir werden auch überlegen müssen, brauchen wir das jetzt? Und dann wird, glaube ich, schon geguckt werden. Wir haben jetzt einige Gebäude, die haben bewusst keinen Keller gebaut, weil sie sagen, der meiste Beton geht in den Untergrund. Wenn wir das weglassen, dann können wir oben mit einem anderen Material leichter bauen. Das heißt, es wird ganz andere Optimierungsfragen geben. Und dann, glaube ich, haben auch solche Ansätze wieder eine große Chance.
Wir haben bei vielen der Projekte, die dann als klimaneutral oder entstanden, gesagt, okay, wir haben jetzt diesen Energiebedarf und also sozusagen als Rest nach unseren ganzen Optimierungsprozessen. Und dann machen sie eine Solarpaneele aufs Dach, um das sozusagen selber zu speisen. Aber es ist nicht oft das Problem, dass ich, sage ich mal, genau dann diese Energie auf dem Dach produziere, wenn ich sie nicht brauche. Und dann Energie aus dem Netz ziehen muss, der dann nicht aus Solar kommt, wenn ich keine Solarenergie auf dem Netz habe. Das ist dann wirklich noch klimaneutral, weil oft der Strom, den ich da ziehe, der kommt dann aus dem Kohlekraftwerk, weil ich, sag ich mal, genau in der Nacht brauche.
Also, eins ist ganz wichtig, klimaneutral oder eine Net-Zero-Bilanz ist nicht autark. Also ich brauche das Netz, um praktisch das Fehlende im Winter oder in der Nacht zu kompensieren und ich speise dafür am Tag ein. Und dann ist die Frage, wenn ich das tue mit ein paar Gebäuden, dann haben Sie recht, dann bleibt es bei Kohlestrom in Deutschland oder importierten Kohlestrom aus Polen in Österreich nachts. Wenn wir aber das ganz viel machen, also praktisch nicht nur das Gebäude selbst ausstatten, sondern auch neue Anlagen bauen, dann wird sich der Mix irgendwann ändern. Und es geht jetzt ja sehr stark in auch speicherfähige Medien und einen sehr breiten Park an Energieverbund über ganz Europa. Die Leitungen fehlen dazu noch und das clevere Management, das Netz so abzugleichen. Aber wir waren praktisch vor 10 Jahren bei einem Anteil der erneuerbaren Energie in Deutschland von 5–6%. Und alle haben gesagt, wenn wir 10–15% haben, bricht das Netz zusammen. Jetzt haben wir 40–45% und das Netz lebt immer noch. Wir müssen aber 80% haben, damit genau das nicht eintritt. Und das geht nur über massiven Ausbau dieser Energien. Deswegen muss man sich an die Dinge gewöhnen. Und man muss die Leitungen ausbauen, weil nur dann hat man eine Chance, dass man so weit verschieben kann, dass das funktioniert. Und dann haben wir Dinge gemacht wie diese lokalen Speicher, die kosten natürlich eine Menge, aber die machen genau dieses Kurzzeitpuffern. Und diese Factory da in Probstzella, die hatte so einen Eigendeckungsanteil ihrer Solaranlage von 40%. Und den kriegt man so auf 55% mit einem kleinen Speicher. Das Ding, was man da sehen konnte, das kann man wirklich kaufen. Das ist teuer für einen Privathaushalt, aber für so einen Laden ist es kein Thema. Das weiß ich, 130, 150 Kilowattstunden. Kostet jetzt 100.000 € verglichen mit dem, was die da gemacht haben. Und damit kommt man schon diese 15% mehr Richtung Autarkie und braucht weniger das Netz als Zwischenpuffer. Und ich denke, das ist das, was wir machen werden. Also die Solaranlagen müssen dezentraler sein, sie müssen näher an den Verbrauchern sein, sie brauchen diesen Kurzzeitspeicher und dann muss man praktisch mit Autos, Laden und Waschmaschinen, all dem clever agieren. Und all das ist im Prinzip keine technische Schwierigkeit, gibt es alles schon. Aber mein Elektroauto redet nicht mit meiner Hausanlage, das können die nicht. Sie können auch nicht zurückspeisen, das soll erst kommen. Gibt es ein paar, die das schon können. Das ist alles viel zu langsam. Und Wenn es denn mal technisch da ist, dann ist es verboten aus Abrechnungsgründen oder ich darf den Strom nicht nutzen. Und also das, was gerade in Deutschland hoffentlich weiter passiert, ist das alles zu ändern und zwar schnell, weil sonst haben wir gar keine Chance. Wir haben eigentlich das ganze Zeug am Start, aber es ist nicht so integriert und es ist auch nicht immer per Vorschrift erlaubt, dass wir dieses Problem, das leider noch da ist, überwinden können.
Wenn wir reden über erneuerbare Energie im Gebäude, ja, die meisten denken an PV-Paneele und so weiter. Aber jetzt sind auch so Windturbine, integrierte Windturbinen im Gebäude, sind eine interessante Lösung. Ja, was denken Sie darüber und wie viel Energie kann man eigentlich verdienen mit ihm? Ja, sind die effizient genug? Oder?
Naja, also wir haben das auch schon gemacht mit Windturbinen an Gebäuden. Da kann man auch einen Beitrag leisten. Das muss gut integriert sein, weil wenn die bei starkem Wind sich bewegen, gibt es Vibrationen. Das ist nicht immer so ein Thema. Das größere Thema ist eigentlich, dass leider Wind etwas ist, was nicht linear mit der Höhe und der Windgeschwindigkeit skaliert, sondern die Kurve geht so hoch. Das heißt, wenn ich mal so eine Windmühle baue, die 250 Meter hoch ist, dann ist da oben Faktoren mehr Wind und auch die Systeme sind effizienter. Das wird ein Problem, wenn ich das alles lokal an der Fassade oder auf Gebäudedächern machen will. Aber es kann ein Beitrag sein, vor allem wenn ich es kombinieren kann mit anderen Dingen. Wir sind aber schon der Meinung, dass wir, wenn wir das große Problem lösen müssen, natürlich alles benutzen müssen, aber wir müssen auch gucken, wo geht es einfach und schnell. Und das ist leider bei den großen Windmühlen und die sind nicht in der Stadt, aber sie sind zum Teil auf Produktionswerken. In Leipzig hat BMW zum Beispiel Windmühlen direkt neben dem Zaun. Und auch VW in Wolfsburg hat Windräder in der Nähe und überlegt, welche auf ihr. Wir müssen sie da einstellen, wo sie im Prinzip nicht so stören. Das, was dann stört, daran müssen wir uns gewöhnen. Und dann können wir all die anderen Dinge tun. Und die Lösung ist nicht ein paar wenige Maßnahmen, sondern eine ganze Suite von Maßnahmen, die wir gemeinsam machen müssen. Da gehört auch die Nutzung von Wind an Gebäuden dazu, ganz klar.
Ja, ich meine, mehr also kleine Turbinen sind zum Beispiel die Vertikalturbinen.
Ja, genau, Darrieux-Rotoren oder so, genau. Also die haben den Vorteil, dass sie weniger Vibration auslösen, schneller anlaufen. Und das kann durchaus eine gute Lösung sein. Das gibt es ja auch auf Höfen, die weit weg sind von allem, dass man dadurch praktisch sich unabhängig macht von dem Stromnetz. Und wenn es dazu führt, dass man unabhängig wird und weniger hin und her schieben muss, dann ist es sicherlich eine gute Lösung.
Die Frage zu den Batterien, gibt es auch eine andere Möglichkeit, Energie zu speichern? Weil es ja auch das Problem mit Batterien oft dabei weg, dass die Batterien so nicht sind.
Ja, also gibt's. Es gibt natürlich die Pumpspeicherkraftwerke, die gibt es schon lange. Da ist man auch bei so Effizienzgraden von 65 bis 70%, also praktisch raufpumpen, runterpumpen. Das ist so ungefähr, wo man hinkommt. Bei einer reinen Batterie ist man bei über 90%, aber man muss die Batterie bauen. Sie hat ein Gewicht, sie ist groß, sie enthält seltene Erden, immer weniger davon, aber sind immer noch drin. Sie ist nicht ganz ohne Probleme, vor allem im mobilen Einsatz, wenn man sehr hohe Energiedichten erzeugen will mit Warmwerden, Feuer fangen, löschen, all diese Themen. Deswegen glaube ich, es wird ein Mix sein. Und was auch im Moment noch wahrscheinlich vollkommen falsch ist, ist, dass wir die Batterien, die man eigentlich in Autos bauen kann oder in Laster, in Häusern einsetzen. Also Lithium-Ionen-Batterien der höchsten Energiedichte. Warum ist die Batterie an meiner Hauswand nicht doppelt so dick und aus einem Material, das weniger Lithium oder gar keins braucht, weniger Energiedichte hat, sehr viel langzeitstabiler ist, weniger Probleme hat, nur einfach dicker und schwerer ist. Für alle stationären Anwendungen werden wir auf solche anderen Materialien wechseln müssen, weil wir haben gar nicht genug Lithium, Kobalt und was man alles so braucht. Und es ist auch so, dass praktisch die anderen Techniken natürlich alle immer konkurrieren, Speichertechniken. Da gibt es auch ganz einfache, das ist ein Heizstab in einem Warmwassertank. Wenn man wirklich Überschussstrom hat, kann man auch thermische Speicher dafür benutzen. Also wir werden das alles integriert machen müssen, gut ausregeln. Ich denke aber, dass wir haben auch Wasserstoffsysteme, also Elektrolyse, Wasserstoff machen und dann eine Brennstoffzelle wieder in Strom verwandeln. Da ist man bei einem Wirkungsgrad, grob gesprochen, von einem Viertel der Energie, die da wieder rauskommt, in Form von Strom, als die man reingesteckt hat. Kann man also nur machen, wenn man wirklich viel davon übrig hat. Dasselbe gilt für E-Fuels, ähnliche Größenordnung. Das heißt, wir werden uns schon für jede Anwendung die richtige Speichertechnologie aussuchen müssen und dann irgendwie haushalten mit Material und eben auch haushalten mit, wie wir die Dinge betreiben. Und dafür braucht es wesentlich mehr Integration und Sektorenkopplung und Intelligenz in dem ganzen System, als momentan da ist. Und deswegen sind wir auf der Gebäudesektorseite ja auch nur ein Teil davon. Aber wie man gesehen hat, ein wichtiger Teil. Also wenn nicht der Gebäudesektor und die Städte anfangen, dann wird das schwierig werden, dass Mobilität und Industrie und Ernährung und all das hinterherkommt. Also es ist wirklich, wenn man sich das so überlegt, also schon eine Aufgabe für die sehr nahe Zukunft. Wenn nicht da sehr viel passiert, dann werden wir hier ganz andere Dinge diskutieren in 10 Jahren, als wie man schöne Gebäude bauen kann. Ist jetzt nicht so ermutigend, aber leider Realität. Aber ermutigend ist vielleicht, dass, wenn man mal kapiert hat, dass das eng ist und so schlimm dieser Krieg in der Ukraine ist, dass uns der Gashahn abgedreht wurde in Deutschland, hat extrem viel Veränderung ausgelöst. Viel mehr, als man sich je hätte vorstellen können. Und auf einmal fragen alle Bauherren nach Gebäuden, die ohne das auskommen und wie das gehen soll. Und sind bereit, richtig Geld zu investieren in erneuerbare Energien und andere Formen der Versorgung. Und ich glaube, das zeigt einfach nur, wenn wir mal die Klimakrise so verstehen würden, wie wir einen Krieg verstehen, wenn man wirklich tot umfallen würde von zu viel CO2 in der Atmosphäre, dann wäre viel mehr passiert. Jetzt müssen wir diesen Lernprozess alle zusammen schaffen, weil es ist einfach fehlende Intelligenz, wenn man ein langsam sich bewegendes System nicht erkennt und entsprechend früh reagiert, dann kommen wir zu spät. Und das ist den Dinosauriern passiert und ein paar anderen Spezies. Das sollte uns nicht passieren. Dafür sind wir eigentlich zu clever. Wird sich zeigen, ja. Gut.
Ja,
Dunkel genug.
danke, Stefan.
Gerne.